Evet, merhabalar. Bu oturumda toplam sunum sayımız 2, 4, 6 tane sunumumuz var. İlk sunumumuz Abdurrahman Al-Rahman isimli katılımcımıza ait. Dear Al-Rahman, are you ready? Dear Al-Rahman, Dear Al-Rahman,
Hi everyone. Hi everyone. Hi everyone. My name is Hi everyone. My name is My paper ID 99. My presentation about and and the report using GPS. Supervisor for for example, in this slide, I also use paradigm for global network
هاي
هاي عرضه مالته ما في صوت. عرضان مالته زينه تبع مالته هاي
according to the patent's plot test without the need of an expert specialist doctor. The objectives. This proposed research will be useful to society and the medical sector for enhancement and improving the health system in the future by using machine learning models with the sickle cell disease datasets are building a model able to learn from the future in the medical dataset that can predict the appropriate treatment doses with accurate amounts. Also support the doctors, hematologists, or beginner doctors to take the appropriate decision and providing the appropriate dose of medication to patients of sickle cell disease. Can be designed a new technology by using a multi-class medical dataset to enhance the healthcare field. Related work. In our research, we proposed a new procedure to treat patents of sickle cell disease by the medical dataset and provide the solutions that help specialist doctors who addresses the following issues. We expanded the scope of work by using 9 classes, represent the doses of the treatment and use the data of patents records with 96 samples. Then we dealt with the raw data sets by pre-processing to solve the remove outliers, entering the missing value and selecting appropriate features. Then used machine learning techniques to the purpose of sickle cell disease dataset classification and a comparison made between them, presenting the result and evaluating their abilities. The evaluation process was carried out using a set of performance evaluation metrics techniques. We aimed to improve predictions of the sickle cell disease dataset to achieve the best performance and accuracy. The description of models which that used in this paper and description sickle cell disease datasets. In our research, applied the supervised classification algorithms because the sickle cell disease dataset has a target values which represent the amount of medication. Firstly, we used logistic regression classifier, considered one of the most popular linear classification models that is used for statistical data analysis and solve classification problems. Second, quadratic discriminant classifier is one of the types of discriminant analysis used as a statistical tools for the classification process, employing a Bayes classifier. Third, naive Bayes classifier is a classifier that depends on a probability and statistics, which assumes all features are independent of one another given the value of the class and are based on Bayes theorem. Finally, we use Leavenworth multi-cored neural network is a tool of artificial neural network required as structurally similar to elements associated with the human brain, which is a collection of neural network called neurons. The description of sickle cell disease datasets. Our sickle cell disease datasets collected with within 6 years for the hemophilia center of the Leather High Children Hospital by the hemologist. The data contains 1896 samples for the records of patterns and 1 target values, which represent the dose of hydroxyurea. Each sample contains 40 features. By using 9 various amounts doses to treat sickle cell disease, the dose increase or decrease depends on the pattern's status and given according to the results of the blood test sample, including 9 classes in milligrams, 250, 300, 1500, 600, 700, 750, 1000, 1200, 1500. The methodology. The design part involves building the purpose model to achieve the requirements for the prototype. At present, the management of disease modification treatment consider that there is no centralization. The goal is to produce and achieve an improved healthcare standard and the ability to use it in various clinical settings. The motivation for doing this method is to evaluate the efficiency and effectiveness of using advanced machine learning algorithms to techniques on sickle cell disease datasets, to predicting the amount of medication for patents depends on their conditions. In order to carry out our experiment using the sickle cell disease datasets, in Figure 1, illustrate the proposed figure for framework architecture of our research. This figure explains the phases proposed methodology framework. Firstly, we take the raw data from the hospital. After that, we make it pre-processing to clean the data from the, for example, detection the outlier and solve missing value. After that, we structure the data because, for example, data integration and feature selection. After that, we divided the dataset into 3 parts: training set and validation set and testing set. After that, we build the model to select the model. After that, test the model by using performance evaluation, for example, sensitivity and specificity and precision and accuracy and receiver operation characteristic curve and the area under the curve. Finally, we will present the results. The outlier detection. In order to represent our data set by graphically depicting groups of numerical data, we're using visualization inspection manner to detect outlier and show it on the box plot by Mahalanobis distance. In Figure 2, illustrate the outlier in the future, which shown in the left figure, where start represent extreme outlier while circle refer to outliers. In the right box plot, removing the outlier. The missing value. In the missing value, we filled the missing values with the mean technique use, depending on the coordinates of the clinicane. In figure 3, illustrate the missing value in the futures. For example, each of future HP and PLTS and MCV and NEUT and the value have gotten with rates lower of missing values between range 0.7% and 1.2%. Appear these features have been a high effect on the amount of medication. And otherwise, each from the future weights of kg with 52.3% and a kilogram with 55.2% and LDH with 40.6% have a high missing value because they not have a large effect on a blood test. The future selection, we solve it by using techniques that use removing or ignoring unrelated future and frequent with less important information. To evaluate the important future of our datasets, sickle cell disease, in order we applied R-squared and root mean squared error technique use. As shown in figure that the bio future obtained the lowest importance. This future has been removed as irrelevant because not impact of hydroxyureatose. The results. This section presents the result of classification for records of sickle cell disease dataset to doses. This is achieved by using 30 future effects on the result of the blood test in order to deal with each model separately for learning. The dataset should be divided into 3 main parts: training set, validation set, and testing set, where machine learning technique use learn from the data of the training set of the training set to perform the task correlational. The validation set provides an evaluation of general performance during the training process. The testing set is used to evaluate the performance of the models with unknown classes labels. The training set and testing set are selected randomly. The model applied in our experiment are logistic classifier, quadratic discriminant classifier, Naive-Bayes classifier, Leeuwenburg neural network. The main purpose of using several classifiers are to evaluate and estimate each classifier which is able to the better performance. In the figure shown at the area under curve histograms the result of classifier training. The training process was performed on each model individually. After that, evaluate was carried out through the metrics of evaluation performance. Shown the result obtained that the Leeuwenburg neural network classifier beat all other classifiers, performed the best accuracy with 0.93 and area under the curve with 0.96 by the average 9 classes. In the otherwise classifiers, logistic classifier and the quadratic classifiers and the Naive-Bayes classifier received poor results through the area under curve by the average 9 classes of 0.80 and 0.87 and 0.67 respectively. In the figure, it's shown area under curve histogram, the result of classifiers testing. Also, the Leeuwenburg neural network obtained a better accuracy by the average 9 classes of 0.84 and area under curve with 0.87, while Neve-Bayes classifier has achieved the lowest result through all area under curve of performance evaluation methods by the average 9 class with 0.60. Through comparison with other classifiers, the Leeuwenburg neural network produced high accuracy. The conclusions. In this research purpose, usage of machine learning models to improve the model medical fields and classify the amounts of the sickle cell disease dose. We used a real data set contains 1896 samples which represent the model test for sickle cell disease patterns to classify 9 classes of the therapy using various machine learning models. The main purpose is to examine the performance of classification models during training and testing phases, and to ensure these models are able to classify the appropriate amount of medication dose according to the patterns blood test. In our research, used different architectures firmware of testing performance for each user model. The result motivated us to apply various machine learning techniques that can offer high results. In the future works, we recommend in the future work usage of genetic algorithm for improvement and physiologic and deep learning that determine the future and modeling automatically and use the neural networks. Thank you for listening.
Thanks for your presentation. Next presentation, Dear Hail.
Hello everyone, my paper title, an overview on binary and non-binary codes and challenges in low parity check density. My paper ID 34. Introduction. The low parity check density LDPC is a class of linear block codes. It is very important to provide the code length and sparse matrix control parity. Both long codes and sparse matrix of parity regulation are effective to meet the efficiency of Shannon maximum. The LDPC codes do include descriptive codes which can be used with statistical data, although long-lasting codes are superior in efficacy. Short-lasting codes are preferred since short-lasting codes are simpler to build than long-lasting. The name of the LDBC code is taken from the matrix attribute for parity power. 2. Error correction codes. In the transmitted bits, the error correction code ECCS are used. This is done by adding extra bits in the signal. The additional bits help to detect and correct errors that are induced by the transmitted signal when the signal is received. Many types of error correction code are available. The number of errors that can be detected and corrected is determined by the error correction scheme. In general, bits means more error fixing capability and higher cost. Error correction code are broken into two categories: linear code blocks and code convolution. 3 types of LDBC-S. A. Binary LDBC. Binary LDBC codes, BLDBC-S, developed a high ability to correct mistakes and channel use for wide stretches of cable. Because of short periods in the matrix parity, the short code word length have worse performance. Binary BLDBC codes have been first discovered with decoding bits flipping (PF) and one-stroke encoding major logical MLG. P. Non-binary LDBC-S. NB-LDBC codes have been shown to work better than short and medium duration binary codes. However, the higher the field order, the more encoder hardware complicated performance. 4. Challenges of LDBC-S. We can list the most important challenges to be solved. 1. High data rate surface, high performance, high delivery rates for buckets, BDRS, low-end latency, and stable infrastructure are a problem. 2. Several channel coding schemes are suggested to address these challenges. The 5G and R design also challenges maintain optimal performance, not only for the complete base diagram, but for shorter version as well. 3. The requirement of converting node connection in a quality layout, the tenor graph, and efficient approach to the problem. In most cases, in instance, repetitive trend of axes are forced a graphic design of the tenor. Weighing appropriate arithmetic to memory instructions ratio, which maximize the LDBC decoding efficiency for the computer underlying architecture and design structures. 5. The complex exploitation of multi-core memory hierarchy, or the complicated problem of defining a suitable LDBC decoder system of monitoring. Thank you for listening.
Thanks for your presentation. Next presentation Dear Luay. Dear Luay.
Hi everybody, I want to present my paper predicting breast cancer in fine needle aspiration images using machine learning by me Luay Al Samarai, Supervisor, Assistant Prof. Dr. Abdullahi Abdul Ibrahim in Altenpash University Department Computer Engineering. Breast cancer is the second leading cause of cancer death in women in the world. Statistics show that 1,152,161 new cases of breast cancer are found worldwide, and with 411,093 deaths. It has been shown that early diagnosis of breast cancer increases the probability of complete recovery and reduces the mortality of patients suffering from this cancer. The fine needle aspiration biopsy techniques is the most cost-effective test for the first-line diagnosis of breast lesion, palpable and non-palpable in a simple and easy way, with a diagnosis yield greater than 90%. In this work, we have designed and implemented a system whose main purpose is to detect the extent of breast cancer lumps in fine needle aspiration images. We use clustering and feature extraction methods such as CNN, which means convolutional neural network, and then we use a classification method to detect the cancer. We experimented with some classification algorithms to choose the best one in terms of accuracy and time in order to base our research on that algorithm. We compare the SVM algorithm with the Bayesian algorithm and naive Bayes algorithm as shown below in these two tables. In this experiment, the result of the classification are shown performed on a set of 40 digital fine needle aspirations already organized as explained in section 4.3, taking approximately 33.33% for the three classes defined in the first group and 33.33% for the classes defined in the second group. In figure below show the 10 best results for this experiment. Conclusion in this work, a mammography lesion classification model was successfully implemented with accuracy metric and approximately 68%. The main limitation of this work was the number of images available. Improving the accuracy metric of training and validation in the parallel until a point is reached where the method begins to memorize the training images. And thank you for listening.
Thank you, presentation. Last presentation, dear Muhammad Salah Aboud. One second. Okay. Dear Salah, there isn't Salah. Okay. Session the end. Best regards.